Welcome. So, the exam is 3 questions, and those questions are taken from Bernoulli, conservation of mass, conservation of momentum, 1 question on each, but kind of mixed up. The overall exam is out of 250, but 100% score is 200, so you can get 125 potentially for the exam. And so what we'll do today, I thought, unless you think differently, is we'll go through the material that's been posted online. It's on Angel. I changed it the other night. What I did to change it the other night, which I apologize for, actually last night, was that I made a more comprehensive equation sheet at the front, and I took out some of the pages that were already in there. So the only thing that's changed is the second page in this, which is kind of the equation sheet that you have. It's all in one place, and I took out some of what I thought were superfluous materials. And so I thought, if you want, we'd go through this, right? So I remember last time also that Lucy told me after the fact that people had their hands up. If you want to ask a question, do ask a question, shout, in case I'm buried in this. I mean, that's one of the negative things I think about using computers and not having a chalkboard, is that you don't, it's not quite so dynamic, right? So, okay, so that's fine? Okay, do that. All right, so, well, you'll see in this, I don't want to give you whiplash, but there's a bunch of stuff that I'll make the main points for. These equations are always written in perhaps the most general way, and maybe that makes them a little convoluted, so let's talk about what they might mean and how we've used them. And so you will see in this that these are written, so we have a couple of equations for Bernoulli. So this is Bernoulli. And this is for a long streamline, and these are for a cross streamline. We've almost never used it, and they're both in either differential form, the first one in each of these, and integrated form, the second one, I guess, if you want to put it that way. And so we haven't used them in those. The main way that we've used them is we use this Bernoulli, and I prefer to write it this way. It's just easier, just because I can think of this. We all have our ways of thinking about things, but I write it in terms of length scales, which are heads, pressure head, elevation head, velocity head, and we know that if you write it upstream and downstream, we've done that as a matter of course. It doesn't actually matter so much in the stuff we're doing in this test, but it will do for the next material that we do, which was, energy losses. And so we've written it in that way. And so this is upstream. This, of course, V1 and V2 equal streamline velocities. So along the path of flow. And we've used that in a variety of ways. I think you certainly used this in one of your examples, example questions. And it's just to be able to look at how things change as you go along. You can write these as finite derivatives, but you definitely need to know Bernoulli. For this question on Bernoulli, you need to know how to use it. You might review your manometer stuff as well. You've certainly done a question with manometers in it. Perpendicular to the streamline, again, we've mainly used this integral form. So what do we have to say about Bernoulli? I guess what we should say is that maybe the coordinate system is z is positive upwards. You know all this stuff, right? So I'm just going through this. And so you write it from some location 1 all the way through, doesn't matter where it goes, to some location 2. And you know that at each of these points, the value of E, so this is equal to E. This is equal to energy. And it's constant along a streamline. And that allows us to be able to solve problems where there's no viscosity present in the system. So we've used that. So I think this is the only important feature of the coordinate system, is that z is positive upwards, and that velocity is positive from upstream to downstream. is what we've always used. So just do that. For a perpendicular streamline, then the expression is almost analogous to this, right? Pressure head, elevation head, velocity head. Pressure head, change in pressure, change in velocity, which is really the change in inertia in the system, and change in elevation. And so in that particular mode, we've talked about a streamline and maybe a parallel streamline. So these are two arcs. VS1. And these define behavior. Well, let me do it vertically because it makes it easier. This is the example we did. You know, we did the example of the car going over a bump, which is the same as fluid going over a bump. You feel weightless when you go over a bump. So if you go down through the fluid column, the pressure change with depth isn't the same pressure change as a swimming pool. It's slightly reduced because you've basically reduced gravity as you go around the hump. So, so the coordinate system for this is in terms of these values, n is drawn towards the center of this circle, center of rotation. This magnitude here is r, and this again, z is vertically upwards. So if I was to draw it from here, I know this is getting to be a nasty figure. Perhaps all my figures are nasty. Z is positive in this direction. N is positive in this direction. And so we did an example which we'll look at a little later. And so the two principal manifestations, if you like, of Bernoulli are going along a streamline, which we've used 90%, I would say, and going across a streamline, which we've used maybe 10%. We did an example to do. And so just be aware of the sign conventions. Of course, the velocity again is positive in the direction of flow along the stream tube. There is this velocity here is not normal to the streamline velocity because, of course, the normal to the streamline velocity is 0. Right? All the flow is along the streamline, so orthogonal to that, there is no velocity by definition. And so I would say that if you're going to look at things, I like this form myself better. Just they're both equivalent, and maybe you want to look at this. We've talked about free jets. We'll go through some stuff, and so yeah, actually look at the free jet stuff because I think that's useful to understand. I don't care about sluices. This, of course, now you're so advanced, you'll laugh at this, right? Conservation of mass. We spend a whole week talking about conservation of mass. So the idea of area times velocity in equals area times velocity out is embedded in your psyche, I think. In terms of, it's just a natural thing to think of. And you remember when we used this was that if, for instance, when you write some system down, you find out there are two unknowns and only one equation, the one way that you can allow it to be solved is to figure out one extra constraint. In other words, link the velocities at the upstream and downstream in some way, so it makes one of these unknowns, if you have two unknowns, go away. Okay, so that's how we've used it. Okay. We spent a bit of time talking about derivatives. I don't know whether I want to spend much time on that here, but you'll remember, you'll remember that basically the idea of a derivative is that whatever the property is, in terms of the material derivative, you just look at how those change, how that property changes. So I'm not going to go, So in other words, you just look at how the behavior occurs in different directions. And so whatever that property is, whether it's, for instance, density, which it could be a scalar value like velocity, then all you need to do is to write it out so that you look at the change with time, with velocity, with a distance in the x direction, say. So we're just multiplying these by 1, etc. And of course this now becomes the velocity in the x direction, and this is the convective acceleration. And of course this doesn't change anything, right? This is just 1. And so we talked about deriving those, and so that's fine. You've done some examples, I think, with those. But the real utility of this was really to make the case that it matters what reference frame you're using when you are considering behaviors, and that's more important, I think, when we talk about these conservation of laws. So, fine. So, I don't think you need to know how, so you can put that on the back burner maybe. So the important things, so we've talked about Bernoulli, most of the stuff is Bernoulli. This is all preamble for Reynolds transport theorem. I'm not going to ask you to derive anything in Reynolds, but we have used Reynolds transport theorem to define behavior for two different systems. One is in terms of conservation of mass, and one is in terms of conservation of momentum. Those systems that we've used, we derived from Reynolds transport theorem, but we used them in a much simpler statement. And the statement for conservation of mass was what? It was density times the rate of change of volume plus the volume times the rate of change of density. Sorry, forget that. Is equal, plus the rate of change of mass is equal to 0. So that, you can certainly get by using that expression in what we're going to attempt to do. We talked about relative velocities, that the velocities, it doesn't really come to play in here, but the relative velocities relative to someone who's a static observer, this is flow relative to control volume. And this is the velocity of the control volume, control surface. I should turn off Skype. Volume or surface, it doesn't matter. Well, it does matter, but for the things we'll deal with in this exam, they're equivalent. That means they're not deforming, I guess. So understand what conservation of mass equation is. Understand what these relative velocities are. And the other thing that we dealt with was conservation of momentum. And again, we had two relatively precise or contracted equations, and those equations were what? We threw away the time-dependent term. Well, let's not worry about this equation. Conservation of mass was what for us? It was velocity times mass flow rate is equal to forces. Actually, the sum of these, right? And I think that's kind of the same here, right? You know that anyhow, but these are applied. And so this velocity is a vectoral quantity, so we have to resolve in x or y or z. This mass flow rate is a scalar quantity and is either in or out. If it's in, it is negative. If it's out, it's positive. We'll talk about that a little later. And so if you want to, so in all of the stuff that we'll talk about in terms of conservation of mass, the one equation that you might want to remember for conservation of mass is this, subject to this. And the one equation for conservation of momentum that you might want to remember is sum of, let me do this, so these. And these are, I haven't underlined them with a vector bar, they are of course, but you just need to think of this as being velocities in the x direction and forces in the x direction, velocities in the y direction, forces in the y direction, etc. So, and all we've done here is we've taken this equation and we just substituted this in. And so this is something you might want to emblazon on your psyche. And just to round things off, we've also talked about conservation of momentum ones. We've talked about these cross products, but really what is the expression that we end up with to write it in this way? It's torque is equal to the tangential velocity times the radius of turning times mass flow rate. Lubisha must have woken up. Okay, this is an equivalent. And of course you can resubstitute for this if you wish as V theta is equal to W theta plus relative motion. And we've used this. We used this in our sprinkler example, if you remember. Okay, so if you're looking to be able to limit the number of stuff you bring to the test, I'm always loath to do this a little bit because I realize that the pressures on you guys are quite large. I'm very actually, I think it's very impressive actually what studious students in the US system do, because you work hard, because there are all these intermediate deliverables, and I guess I have a less intermediate deliverable system, that we don't have super huge numbers of assignments to do, but we do it on the exam. So I appreciate that you are trying to just get through, right? Get through the marathon, and so you are relatively busy. And so, but anyway, so you'll see this online, and you can come back to these. But Bernoulli, you need to know for sure in a couple of different forms. Conservation equations, you should know for sure in the reduced versions that we've used, and understand exactly how to make these transformations, right? So that's the first part. So at least it helps you narrow down some of the things that you've done. I'll just go through some of the examples. I guess I'll try and point out the important features of these because we can't really go through them. I think that maybe limiting this to a number of examples in this little text that we have is helpful to you because you can go through it and look at it at your leisure. I'll just try and point out the main features that I think are important that you should be thinking about when you do this. So if we look at perpendicular to a streamline, we kind of drew the figure. I'm not sure whether you could understand very well from my figure exactly what it was. But the idea of looking at behavior along a streamline is that, of course, the velocities you're looking at are the streamline velocities. And this would be the streamline velocity at point 3, and this would be the streamline velocity at point 4. The velocity normal to those is 0. And we talked before about being aware of the two coordinate directions. Z is always positive upwards, but the n direction, which occurs here, as you write these at two different points, is always written positive, pointing towards the point of rotation of this, right? So this is the center of the circle, and this is the, so in this case, this is the point of rotation here. This is R. And R is always a positive number. And this example was just going through the calculation using Bernoulli, and basically, if you scan down to the bottom, we were making the point was that if you look at the pressure at point 3, which is this point below the water. So this is the surface of the water. If you look at, this example's in the book as well, so you can look at that. If this is the surface of the water, which is a streamline, of course, and it's going over a hump, then if you look at the pressure you'd feel at this point, if your ears were there, it's equal to the unit weight of the fluid multiplied by the depth below the surface that you are, but it's reduced by some small amount. If the radius of curvature is infinite, in other words, it's just going horizontally, then this term would be 0, right? Because this term would be nothing. But if it's finite, as it is in this case, then it reduces the pressure. And so I guess if you drew that out, what you'd get is if you looked at this curve relative to the bed here, if you looked at drawing the fluid pressure with negative Z, and you looked at this being pressure, then if it was static, whoops, it would be this. And if it's non-static, it would be this. Static or flowing horizontally, I guess, right? Without a bump, I guess. So not a great figure, but you get the point. So no, Bernoulli, well, we've talked about it. You've done enough of these things that I'm not sure that we need to belabor this. I never write it this way. I always divide through by unit weight, just because I find that easier. And get rid of these, of course, get rid of this, and that's it. But definitely know how to use that. Know that it has to be constant along a streamline. I think you do know that. Know physically have a feel for what it means. In other words, this magnitude here, of course, relative to any datum, this is what we've called uppercase E, the energy grade line, EGL, I guess, and they might mention in the book. And that is if you add up the components of elevation, pressure, and velocity, they should all add up to the same hydraulic grade line in this particular case, if you're killing velocities. Okay? We used Bernoulli for a number of things. One of the things that we used it for were, for instance, free jets. And to do that, we just did exactly what we've talked about. You write the Bernoulli between 2 points. What do we need to know? Well, we need to know, the tricks of the trade. The tricks of the trade are if someone says a large tank, then that means V1 is equal to 0, right? You know that now. You know if it's a free surface, then you know the pressure is equal to 0. You know that for all intents and purposes, if a jet comes out into the free air, then the pressure also is equal to 0. And if you use this to be able to write Bernoulli and throw away the other parts, what you end up with in this case is a free jet, equation of a free jet, which is just the velocity is proportional to 2gz. And so the other thing you'll remember, maybe you remember from last time, which is the Froude number, which is what? Not on this test, of course, but just linking this together. If you divide one of these things by the other, throw away the 2, the Froude number is just basically related to this. And this is the influence of inertial terms and the role of gravity in driving flow. So unlike in a petroleum well, say, you drop the pressure, you drive the fluid pressure that's pressurized in the reservoir, and it's that fluid drive that drives it. In groundwater applications, the flow is driven basically by gravity. If you're pushing a ship through the water, the bow wave that resists flow is a function of gravity, and so this is an important parameter for that. Not that you need it in this test. What else do you need to know? Well, I guess the other thing is you could also write this equation for flow like this. And I think you'd find that the velocity out of here is also this, for instance. And so it doesn't matter what the orientation is, it's just along the streamline. So it's along the streamline here, and it's along the streamline here. So Bernoulli is always written along the streamline. Okay, so you know that. Okay, this has certainly been on a previous exam. That probably means it won't be on this exam. But the tenets of this, I think, are important. You can write Bernoulli between a couple of different points and then start solving for it. The main tenet, I think, of this that's important is to realize that you can divide velocities into velocities in the horizontal direction and also the vertical direction. And so if you know what the velocity is, and we've used this before, so you should bring your trigonometry to class as well. And so if you know this is velocity here, then you know this is Vx is equal to V cosine theta. And Vy, or Vz, I guess, is equal to V streamline sine theta. And so you can decompose velocities into their components, which is sometimes important. It's important in this case because you're asked to find out the location where it peaks. And of course, the location where it peaks is where Vz is equal to 0, right? That height. And so you can use that to be able to figure out exactly the behaviors of these systems. And so being able to decompose things in some interesting way is useful, and so you should know how to do this. And you should also know when you design your conceptualization, if you like, of what you're looking at, that you know what you're, just have a feel for how to do this. I think that comes by just kind of having a feel for the fluid mechanics of the system. So the deal of this point is that where the velocity is equal to 0. So be able to rationalize how you can subdivide distances. This, of course, is too trivial for you now that you've been looking at conservation of mass. But the point is, if you have an equation where you have 2 unknowns in this particular equation, and of course you can only solve for one, is you can link V1 is equal to V2 A2 over A1, for instance. And depends which variable you want to eliminate. But that's one way to, and you've done that many times. We've done it many times in class. Okay? And so you know that. We talked about flow rate measurements. I just crossed that equation off the sheet, but it really just comes from Bernoulli's equation. I mentioned certainly manometers, I guess we did in the last segment, but certainly they're part and parcel of measuring the pressure drop. So I guess we made the point that when you're looking at measuring velocities, one easy way to do it is to measure pressures and use those pressures to be able to relate to a flow rate or a velocity. And so manometers are important in that. And so I won't go through the manometer equations, but you remember the rules. What are they? As you go up, you subtract, yes, someone said decrease. You go down, you add pressures. And you have to figure out exactly whether the velocities are zero. In this particular case, the velocity would be zero here, stagnation point, but the velocity here would be equal to V2. And so manometers are just a way of being able to measure the pressure drop between two places. And usually, using Bernoulli, you can use that to figure out what the velocity is. So I guess I discarded these equations because you can't necessarily, don't look for the equation that you use to fit into it. Use Bernoulli if you have a question like that. Yeah. And so that's an important concept as well. So I realized, so actually, you know, you should be proud of yourselves. We've gone through about 100 and something pages of my handwritten notes in this kind of sequence of Bernoulli, conservation of mass and conservation of momentum. And so I've tried to whittle those down to about 20 something pages here that you have. And the same deal as before. These, I'm not trying to steer you in the wrong direction. These do include all the concepts and equations, for that matter, that you'll need to thrive in this particular exam. Talked about control volumes between fixed, moving, and deforming control volumes. We went through some examples. I don't think we'll go through those again today, but other than make the point that, well, we'll go through them slightly. Has anyone had their hands up or anything? I've been concentrating on other things. We mentioned that this is the one expression that you probably need to keep in your mind. We know that there are multiple ways to skin a cat, as we've said, in terms of looking at control volumes, and there are a bunch of ways that we did it. You can choose the way you wish to do it yourself for the question that we're dealing with. I suppose the sign conventions you have to worry about or know about is if volume increases is positive, you know that. If density increases, it's positive, higher density. So water has a higher density, yeah, it changes in time. So if it becomes more dense in time, then it increases. Of course, if it's a liquid that's in the system, you don't really care about that because it won't change density very much. And we have this issue of mass flow rates, in that mass flow rate in equals negative because of the dot product, and m dot out is equal positive, right? Because of the alignment, if you like, of the normal to the boundary here and the velocity, the direction of flow are both aligned, and so if it's out, the dot product is a positive value, and you can just use the scalar value of, well, what's mass flow rate is what? It's density times velocity times the cross-sectional area. So you want that written. And you know that. But just remember the sign convention and remember why it is the way it is. Okay? So we talked about different control volumes. We've used a syringe question before. That's not on there. I'm not sure what else I should say about that. No. So, well, I guess the other thing is that I said before that the better way to think of this is to think of it as volume times density change plus density times volume change plus, I guess, yeah, all right. I'm just writing that out, okay. A little bit of brain burp there, don't worry about it. These are relative to the volume, relative to the control surface. I didn't mean to scribble on that. Relative to the control surface magnitudes. And so, yeah, you don't need to use it in any other form other than that. Okay? All right. And maybe the more taxing one is Newton's law for Reynolds transport theorem representing Newton's second law. Again, the way we'll use it is this. I think you might be better off writing it this. So this is the velocity relative to the static. So in this particular case, V static is equal to the velocity relative to the control volume plus the velocity of the control volume. So if you write it out in that form, then it looks like this. W plus VCS, which is this term here, times mass flow rate equals sum of the forces. And if this is in the x direction, this is just one equation, then these both would be the relative velocities in the x direction as well. Right? But you have to resolve. And so we don't have any problems where there's time involved. So this equation, if you know how to apply it, will definitely get you through any question on linear momentum. So get that, or come back to the movie and have a look. This, it says important at the top for a reason. It's the kind of tenets of what we're dealing with. So because the velocity into the control volume is a vectoral quantity, then if you look at the mass flow rate relies on the dot product. And so the dot product of the velocity out plus the normal to the boundary is positive if they're both aligned in the same direction, hence they're positive. If the velocity into the volume is in the opposite direction from the outward normal, then they're negative, and so this is negative. Right? So this is what's used in the mass flow rate is equal to V dot n, right? Remember, this is what we've called the velocity and density and area. So remember this. If you multiply it by the absolute magnitude of the vector, so the vector now is defined positive in the x direction, and in this case, the flow in is positive, so this term has to be positive, even though this term is negative. So the net product of those is negative. And likewise, the stuff coming out here, the mass flow rate is positive because it's coming out, which is this. And the velocity coming out is also positive. Did I say negative? The mass flow rate coming out is positive, as we've seen here, and this is positive, and so the resulting one is there. And so that is perhaps the most important item to keep in mind in your bookkeeping for these problems. And so to think about that and understand that. We've always done relatively straightforward examples with flow across some kind of area and diameters, but we did some examples here. And so all you have to do is to remember to make sure that when you're doing these calculations, that you look at all the forces applied on the body, all of the velocity, changes in velocity, which is the momentum change, which results in a force change in the system, and account for them and resolve in the appropriate directions, x or y. And that's all we did in this particular case. You just have to be careful to do the housekeeping. So in this particular case, we would have a pressure which acts at this upstream location. Stop it. Which you can calculate. And as you do your free body, this is a pressure. There's also velocity. I guess this would be pressure 2. And there's a no pressure here because it's coming out, because it's atmospheric. And you can therefore disregard that, but you can't disregard this velocity. See you, Cooper. How you doing? And you resolve forces. And so you resolve for the velocities going in with the appropriate sign convention. You resolve for the pressure force, which is in the positive x direction, which is this. you resolve whatever the pressure force is at point 2, which is 0, and you have some reaction here that you probably want to solve for. So here you know all these other parts and you know the forces, and you can do it in terms of resolving it. If you don't have enough variables to be able to solve this, then maybe you need to solve, if you don't know what the both velocities are, maybe you need to figure out those velocities in terms of conservation of mass. And I'm trying to think whether we did that in an example. We did that for the decapitated tank example. We used Bernoulli to be able to write the velocity coming out of the thing and calculate exactly what that would be. We used that in the previous exam, so that's not... Yeah, go ahead.
Could you explain why there's no y forces?
There are no y forces because there are no pressures acting in the y direction. So the control volume here, so if the control volume goes around here, and we draw it out over here, then inside this control volume, there's a pressure acting here, and there's a velocity acting in this direction. Here there's no pressure acting here because this is 0. And there's a velocity out. So all the forces and the velocities that you have are acting only in the x direction. Nothing else. I guess the only force that's acting in this direction would be the weight. There would be weight. There's just the weight of the fluid. But there are no changes in momentum, even though it's going around this bend, because we've drawn the control volume, and we're only interested in the boundaries, flows across the boundary of that control volume. So that's the reason for nothing in the y direction. And actually in this case, the y direction is the horizontal direction. So xy, so this monitor or this thing is actually in this plane, not in this plane. So there is no weight in this particular case. If it was standing up, then there would be a weight. And that's a good question, good thing to know. We've talked about moving control volumes as well. That's why, that's why I would say that you possibly want to write this expression that we had for conservation of mass, not necessarily as this, but maybe as this. Where this is the relative velocity of the jet, this is the velocity of the moving control surface. Let's see, if steady state, then V, the velocity of the control surface times the mass flow rate equals 0 de facto, right? And that is because the amount going in has to equal the amount coming out. If the vane, in this case, isn't deforming, it could be moving but not deforming. So in other words, the inlet is going just as fast as the outlet. So in other words, this surface is going just as fast as the outlet. Then you can imagine that the same amount is coming in here as is going out here. The velocity of this point is going in the same velocity as this point, and therefore the product of these two, they're exactly equal to each other at inlet and opposite to each other at outlet, and so this equals 0, and so this becomes W m dot equals F, in this particular case. So it's relative velocity, which is important. And so this example goes basically through that. You can resolve the different forces. In the x direction, you're applying a force to keep it from moving, which is Rx. I guess this is Rx here. And if you write the equations for the inlet, density times relative velocity times cross-sectional area, this is negative because it's going in, hence this term here. This is mass flow rate in. This is m1 dot. The mass out is this amount here. Density, velocity across the control surface times its area. This is m2 dot. But the absolute magnitudes of this relative velocity are equal to this magnitude W that it sees. So it's coming, I think it's coming to you at 100 feet a second. We're moving away at 20 feet a second. So in that particular case, you see it coming to you at 80 feet a second, right? If you're standing still, it would hit you at 100 feet a second. If you're moving 20 feet a second backwards, it hits you at 80 feet a second. And so this is the relative velocity here. So this would be 80 feet a second. And it goes out of here at whatever the velocity is across here. This has to be 80 feet a second. And so the component of that in this direction is, this is W2. And this is equal to W2 cosine theta, which is this term here. So this is W2 in the x direction. So you have to resolve in those directions. And so, yeah, so think about that. So there, so I covered up the microphone. There will be a moving control volume question. So that's linear momentum. You should probably take note of when I covered the microphone, if I did again. And so the other thing that we've done is we've looked at rotational conservation momentum. And yeah, we don't need all that stuff on these. I can put it down here. Is there are two equations of interest to this. One is written at the bottom, and the other one is that the torque that you apply is equal to the tangential velocity times the radius at which that velocity is squirting times the mass flow rate. And again, you can use this into here as we've used. We did a quick example on that. And I guess this is useful. I think this applies also to linear behavior as well as rotational behavior. We talked about being able to figure out the two ends of the spectrum. You know, we talked about a buoy floating in the water and how much energy would come from that. If the buoy is unrestrained, it bobs up with the waves, and you get a displacement or a velocity, but you don't get any force applied to it. If you anchor it, you get a force applied to it, but you get no displacement. And in both of those cases, there's no work. Those are the two end-member behaviors. The equivalent for this would be if you hold this vane static, the water comes in, you have to apply a force. There's no, you're pushing against it, there's a force, but there's no work done. And the other case is if you let it run freely with no force, in which case you can't get useful work from that either. Same for the sprinkler, right? You hold it static, the torque, the control volume is static, so you can calculate what the magnitude of this torque is, because the velocity that you're applying of the control volume is static. Well, the opposite is if you let it spin freely and you don't have to apply force to it, no torque to it by definition, but it spins at some equilibrium velocity. If you wanted to use that for energy, you'd have to do partway through it. You'd couple something to it to be able to apply force, which would be the armature of a generator, and it would go faster than if it was freely spinning, so it'd be somewhere in the middle. And so in addition to the two end members, yeah, we can basically use it to be able to figure out what the force is we have to apply to hold it in place, or what velocity it will go at if it spins freely. Or as in the case, and you could certainly do that in the case of this moving control volume question. In this particular case, it says it's moving at 20 feet a second, but of course you could do the end members. You could say zero velocity, what's the force that's applied, and calculate what the Rx is. Or you could let it just run freely on frictionless wheels, so there's no force, and you'd figure out exactly what the velocity would be that it's traveling at. And so if you go through that in this particular case, you'd find out that, well, what would happen if you dealt with this equation? You could rewrite this equation, for instance, in some way. And if you rewrite this equation, you'd end up with W1, if you take that out. And this is a negative and this is a positive, so this would be 1 minus cosine 45. And you'd end up with density W1 times A is equal to Rx. And so Rx is the reaction. We've defined it in this particular case pointing to the left, which is in the opposite direction to the positive x-axis. Our definition, and so we know the direction which is applied. And if this, for instance, is equal to 0, which this question doesn't do, then the only way that this is equal to, is going to be equal to 0 is if this magnitude here, W1, is equal to 0 as well. And the only way that this can be equal to 0 is if this is going at the velocity cs, which is equal to the velocity of the jet. Right? Bless you. And that was kind of a theme in what we talked about before for the sprinkler. Someone came up after class. So if you have a sprinkler going around, it's squirting fluid out. It depends on what your viewpoint is. If you look down on the sprinkler and allowed it to turn freely, then you'd see this stuff coming out. The water coming out is static, right? The sprinkler's going around at some velocity. The water is squirting out at some velocity equal to that velocity. And so if it's angled at tangential to the circle, the water would just stick there and drop. If it's pointing out from the circle, then you would look, if you used a strobe light to follow that droplet of water, it would just be going radially outwards, away from it. So, I think I'm getting, you don't need to know this stuff for the test, necessarily. And we did a question with a sprinkler to show that. No turbine questions. This is a summary of all those relationships we talked about. I think that's superfluous because we talked on the first sheet about exactly what the equations you might need would be. And so look in detail at Bernoulli, know how to use that. Look in detail at manometer equations, and look in detail at conservation of mass, which doesn't help you too much, right? And also conservation of momentum. The questions, I think, are split 90 points, 60 points, 100 points. And I'm thinking that the 90 is Bernoulli, the middle one is conservation of mass, which is less points, but very straightforward. And the other one is conservation momentum. So no, I haven't really taken very many questions. I did see one hand up, but other questions? It's Tuesday night, 6:30. It's an hour, 90-minute exam, so 6:30 till 8:30, and then we'll start kicking everybody out. Well, we'll meet on Monday anyway. I guess the next assignment is live. I don't worry about if it's a burden, we can push back the due date for that beyond Thursday. You should let me know whether that's the case or not. It just means that the other stuff gets stacked up, I think. But we're in pretty good shape on this. Lucy will be around on Tuesday. I'll be around on Monday. I'm around today. If you want to chat. Okay? Thank you.